In 1957, the Soviet Union launched the Sputnik satellite, the first man-made object to be placed in orbit around the Earth. This animation shows the increase in the number of satellites and other objects larger than 10 centimeters in orbit up to the year 2019. And this animation depicts the current congestion in orbit around the Earth. The distances are to scale, but the object's actual sizes are much smaller than can be depicted here. The greater portion of these objects are arguably the result of unobserved collisions between satellites or rocket components that were placed into orbit. Since orbital velocities may be as high as 7.5 kilometers per second, with relative velocities between any two objects potentially higher, the collisions between orbiting objects are almost always high-energy events. Such collisions may result in perhaps thousands of fragments, all still traveling at orbital velocities. Each of those debris fragments may collide with other objects and perhaps in turn cause still more fragments. As of 2023, there were 34,000 objects greater than 10 centimeters being tracked. Objects smaller than 10 centimeters are much more numerous, but we lack the technology to track them. The European Space Agency estimates that currently there are at least 900,000 objects larger than 1 centimeter and 2 trillion objects larger than 0.1 millimeters in orbit. We can assume that most of those debris fragments are the result of unobserved collisions that have occurred. The chain of events where the environment around the Earth becomes increasingly dangerous due to the uncontrolled spawning of high-speed debris particles has been called the Kessler Syndrome, in honor of Dr. Donald Kessler, who first sounded the alarm about the danger that space debris would present. But the Kessler Syndrome doesn't refer to some future possibility. The Kessler Syndrome is well underway. Space debris already represents a significant hazard to equipment and personnel in space, and it's steadily getting worse. A small fleck of paint caused this damage to the Space Shuttle's window in 1983. Now, spacecraft must be commanded to make frequent maneuvers to avoid debris, but nevertheless, occasionally satellites are damaged or destroyed due to impacts. The greatest threat is from debris particles that are too small to track, yet are large enough to do significant damage. That describes millions of objects, and many of those space debris objects are in orbits that may last for thousands of years. It is only a matter of time until humans are killed as a result of an encounter with a large enough piece of space debris. The Challenger explosion caused the death of 7 astronauts. That resulted in a 32-month pause in manned spaceflight by NASA. There are plans to have dozens or even hundreds of vehicles like this one loitering in orbit for weeks before heading off to Mars. How would we respond to the loss of a spacecraft with 100 Martian colonists on board? Currently, rules are being discussed that will require more responsible use of the space environment in order to reduce the risk that any new launches will create additional debris hazards. Also, various entities are developing methods to capture and deorbit larger objects like non-functioning satellites. But the enormous cost of dealing with space debris is something the international community has yet to commit to. All the solutions under consideration would only address the largest objects, which are themselves only the smallest part of the space debris problem that we face. Consider the following. This BB pistol launches 4.5 millimeter steel spheres that weigh approximately 1/3 of a gram at a velocity of 150 meters per second. A BB is much less massive than the thousands of greater than 10-centimeter objects that are currently being tracked. The kinetic energy of a BB traveling at 150 meters per second is 4 joules and would only penetrate a few centimeters into human flesh. That's not a lethal wound, but one that would require medical care. It is estimated that the average relative velocities of two colliding objects in orbit would be around 10 kilometers per second. A BB striking astronaut at that velocity would have a kinetic energy of 17 kilojoules. That's the equivalent of 4 grams of TNT and would cause a devastating and almost certainly lethal wound after striking any part of a person in a spacesuit. There are millions of debris objects larger than a BB in Earth orbit now, with more being added continually. This video introduces a novel approach to address the threat of small space debris. What you see here is a model meant to illustrate the operating principle of a device that could potentially reverse the major component of the ongoing Kessler Syndrome. This 1 cubic foot target is loosely packed with 150 grams of low-density polyethylene film. Of 11 shots from the pistol, 5 made it all the way through. That ratio is an indication that the target was well matched to the task of stopping the BBs. But then another target that was 1 meter in diameter, also loosely packed with low-density polyethylene film, stopped all of the BBs fired at it. A much more densely packed target could have been much smaller, but the pistol's aim would have had to have been much more precise to even hit that target. The low-density, 1 meter in diameter target was able to stop haphazardly fired BBs coming from any direction. Even a glancing hit from a BB was likely to be absorbed by such a large, low-density target. That example demonstrated that the larger target had a greater probability that a random projectile would be absorbed. If the ability to stop a projectile traveling at orbital velocity is proportional to its kinetic energy, then in order to barely stop a 10 kilometer per second BB, a cube with the same construction as this one would have to be about 1.5 kilometers on each edge. Debris objects that are much larger and heavier than a BB might only lose relative velocity as they punch through such a target, but smaller objects would be consistently absorbed. Even if a piece of debris passed entirely through a target, that would increase the likelihood that a subsequent encounter with that or another target would result in the capture of the debris. But fortunately, the ability of a target to stop an orbiting debris particle is not entirely proportionate to these low-velocity demonstrations. The action of what is termed Whipple shielding, wherein thin layers of a shield material and the debris particles themselves are vaporized upon impact, convert the concentrated straight-line kinetic energy of the space debris into a more random and diffuse form, greatly reducing the required size and mass of the shield needed to stop a debris fragment. The Earth's low-density upper atmosphere works in a similar way to absorb space debris. The kinetic energy of high-velocity debris particles is transformed into enough heat to vaporize most debris long before reaching the Earth's surface. The proposed Space Garbage Collection Target, or SGCTs, are devices meant to achieve the same result as the Earth's atmosphere, but at any orbital altitude. An SGCT is a large, low-density target that would passively absorb space debris and reduce the probability that debris will strike spacecraft. The key attributes of the targets are that they are large, possibly ranging in size from meters to kilometers in diameter, so that they are more likely to encounter space debris. The targets need to be low density to make a large volume more feasible to deploy. Since the threat of collisions is essentially random, reducing that threat requires a reduction in probabilities. That reduction would approach the ratio of the combined cross-sectional areas of the spacecraft being protected to the cross-sectional areas of targets sharing the same orbit. For example, to protect satellites in a communications constellation, one or more SGCTs would need to be deployed in the same or a nearby orbit as the group of satellites to be protected. This illustration is not to scale in any way. The ratio of the targets to protected spacecraft isn't representative in number or relative sizes. The targets in each orbit should collectively have a cross-sectional area that is many times the cross-sectional area of the group of spacecraft to be protected. Since the Kessler Syndrome is a long-term problem, it will require a long-term solution. It may require centuries to address it to the point where the threat becomes negligible. Therefore, the SGCTs need to be composed of a target material that will not degrade in space such that it becomes ineffective or that it becomes an additional source of debris objects. Results from NASA's Long Duration Exposure Facility experiments, or LDEF, suggested that PTFE film was a good candidate for the target envelope material since it survives well in space and is non-frangible and wouldn't create additional debris particles after an impact. But PTFE is high in cost and would be an environmental concern if a large target that was entirely composed of PTFE eventually burned up in the upper atmosphere or survived to fall upon the Earth. Working with the models provided the notion that cellulose may be the ideal material to deploy as the target medium. Cellulose, if protected from ultraviolet radiation, survives so well in space that there has been serious discussion of using wood in constructing satellites. Cellulose is inexpensive and can be reduced to a particle size that wouldn't become a debris hazard if any were pulled away from a target due to impacts. Small particles of cellulose, when no longer part of a target and exposed to ultraviolet radiation, would quickly degrade into their molecular and monatomic components. An entire target filled with fine cellulose wouldn't be a concern either if it one day re-entered the atmosphere. Large rolls of a suitable paper could be compactly carried into orbit, where a fairly simple mechanism could then shred the paper to whatever particle size is desired, and then propel those particles as a stream into an envelope to create a target. The large cargo capacity and low projected cost per launch for the SpaceX starships now in development would make the deployment of a large population of SGCTs into orbit an achievable outcome. To make the threat from space debris a negligible issue may require hundreds or even thousands of targets in various orbits. A single starship will have the cargo capacity to deploy an approximate 30-meter diameter spherical target with about the same density as the demonstration models in this video. If a larger target makes more sense, subsequent launches could bring up additional target fill material, or perhaps higher or lower densities would be optimal. A possible strategy to maintain uniform dispersal of the fill material would be to slowly rotate each target on an axis that is inclined relative to the orbital plane, thereby using the gravitational gradient to distribute the material and maintain envelope shape. Equatorially mounted solar-powered ion thrusters could, when pulsed appropriately, provide for station keeping. Small quantities of the fill material could even serve as reaction mass for the ion thrusters. But these design considerations are beyond the basic invention idea of deploying large, low-density targets to passively absorb small space debris. The exact materials, target sizes, orbits, deployment strategies, target structure, and fabrication techniques are all beyond the scope of definition for the large, low-density, passive garbage collection targets being described here. Yet I believe that along with active, large debris removal methods, using such targets to passively absorb small space debris is the only practical way that the ongoing Kessler Syndrome we face can be stopped and reversed.